Alright, this is the first lecture in a series of Introduction to Thermal Fluids. And it can be thought of as an introductory engineering course, engineering analysis. Alright, let's first start by discussing what a fluid is. There's four states of matter: solids, liquids, gases, and plasma. Right now we're going to be focusing on the first three: solids, liquids, and gases. And let's discuss the differences and compare or contrast the differences between fluids and solids. Alright, first, so fluids versus solids. Let's talk about how they're going to be different. Well, first let's do a demonstration or show a liquid and a solid. Here we go. State measure is a solid. What I have in this glass is water, and that's a liquid. Simple, basic enough understanding. But each one reacts differently to different things that are the physical environment that it's in. The first difference that we're going to talk when we talk about fluids and liquids versus solids is their reaction to shear, or also known as tangential stress. Alright, what's tangential? In your math classes, I'm sure you guys have talked about a tangent line. It's going to be something that is parallel to a point. If you have a graph, tangent line is going to do something along like that. The normal is going to be perpendicular or orthogonal. But we'll deal with perpendicular as different than the tangent line. So let's talk about what shear stress is. But even before we discuss shear stress, let's just discuss what stress is in general, besides what you feel sometimes when you're in there getting ready for a final. Stress. Stress is going to have the units of pressure. So we define pressure from your physics class or your chemistry class as force over area. So pressure is going to be force over area, and we're going to represent that as stress. We'll represent that with the Greek letter sigma. Let's look at what that's going to be. If we have a stress that is going to be perpendicular, we'll see the deformation that we get. So here we go. Apply a force, and I'm applying it over an area, and you see I get a deformation, how the solid reacts to normal stress, perpendicular. And the solid has static deformation. So, we've discussed what pressure is, a force in newtons over an area. We're going to also have the same units as sigma, which is going to be our perpendicular or normal stress. But we want to talk about tangential stress. So that would be the case where we have, again, a tangent line. Tangent or parallel to a point. The computational fluid mechanics and heat transfer book. How convenient. Alright, so if we had perpendicular, we would do the stress in this direction. Tangent is going to be along the surface. So if we have a tangent stress, we get what's called shear deformation. It's going to be different than if we had perpendicular. We're going to represent this as a drawing on the board. So, we have a square block, and we have the force perpendicular to the area, perpendicular. The result is going to be, depending on the elasticity, but that's going to be for a solid. That's going to be the way it's going to react. And if we had, now going, focusing on, this is going to be shear, or our tangential stress. The result is going to be something like that, represented by that computational fluid mechanics and heat transfer book. Alright, that's what happens with a solid. Everybody has seen that or understands that physical process or phenomenon. So a solid resists by static deformation. Okay, enough said about solids. This is a thermal fluids class. Let's talk about what a fluid does. Fluid, when a shear or tangential stress is put on it, results in motion. So it moves and deforms moves and deforms as long as the stress is applied. What does that mean? Alright, well, just so happens I have that same cup of water. There we go. Cup of water. Right now, minimal amount of shear stress, but if I twist it, I'm going to put a force on it due to by gravity, and therefore you can see it's moving along that axis. Therefore you're going to have motion. Putting a shear stress on it due to gravity. Motion. Or moves such as that. Well, this is going to be our normal stress. Let's represent shear stress as tau. It's going to be the force over the area, force that's going to be tangent to the plane. Okay, so now what we've done is we've talked about the way a fluid reacts to shear stress. But fluids are going to be, or are, a larger topic than just liquids. Fluids can be liquids, or as well could be gases. So what a liquid is going to be closely packed molecules due to strong intermolecular forces. Alright, so reviewing chemistry, if you have strong intermolecular forces, those are the forces between molecules. And depending on the temperature you're at, you'll have a liquid. So if we represent hydrogen bonding with oxygen bonded to hydrogen, this is going to be the partial positive, partial negative. There's going to be a connection or I should say an attraction between those partial positives and partial negatives. Intermolecular forces are going to be strong with liquids. causing this to retain its volume in a container. Okay, a liquid retains its volume in a container. This is the container. I have the same amount of volume as I do right now, besides evaporation that you will be occurring, but for the most part, the volume is going to be the same. Also forms a free surface in a G field. This is going to be this top surface that you have right here. Free surface, gravitational field pulls it down, and you're going to have that as a free surface. The other type of fluid is going to be a gas. Gas has large space between molecules due to weak intermolecular forces. Which results in the expansion to fill a volume. If you have a tire, you poke a hole in the tire, the air expands to fill the volume. So if I have a volume in a balloon, sits there, if you poke a hole in it, the air flows out to fill the larger volume. This can be represented if we have our liquid in a container. This is our free surface. If we have this as a container, these are the molecules that spread out to fill the container, and if we open it up, the gas molecules will fill up the rest of the room. Right now we've discussed solids versus liquids, or solids versus fluids, as well as two different types of liquids. We have, or fluids is going to be liquids and gases. Well, let's talk about specific differences between types of liquids and different types of gases. This is going to be your homework assignment to explore different types of liquids, household liquids, and a demonstration will be coming, a video lecture of that, going through it. Alright, so fluids. What's going to be the difference between different types of fluids? One particular material property that's very, very important, I'm starting in a different place than most people do, but it's going to be viscosity. So fluids. What's the diff? What's the difference between different types of fluids? The thing we're going to be focusing on today is called dynamic viscosity. Dynamic viscosity, I'm sure during car or oil commercials you've heard the term viscosity, thermal breakdown, and terms being thrown out. Well, we're going to discuss viscosity, and then again do a demonstration and a homework assignment based on getting to be familiar with different types of viscous fluids. Dynamic viscosity is going to be given by the Greek letter mu. Greek letter mu represents dynamic viscosity, and it has the units of a Pascal times a second. A Pascal is going to be a unit of pressure or stress. Second is going to be a unit O time. So let's again recap if you have not had a physics class, or if you did, well, this will be a review, and if you didn't, then this is what we'll have. A little discussion. So let's talk about pressure. Pressure and stress is going to be a force over a particular area. So again, this is going to be a surface area. And if I put a force across this surface area, I'm going to have pressure on it. In your tire. Generally, you pump up your tires in your car to, let's say, 35 psi. Psi stands for pounds, which is a unit of force per square inch, represented as that. That's going to be your pressure. Other units of pressure are atmospheres, pascals. Pascals are going to be mostly working in, say, unit in the metric system. But, again, it's always a unit of force over an area that the force is applied to. Again, this is normal stress, but I can also put shear or tangential stress to see the result of this particular deformation. Different types of deformation depending on the direction of the stress compared to the area. It's an important difference. Alright, force. Force we're going to be measuring in the metric system is going to be newtons. The area is going to be a meter squared. Let's get an understanding of what 1 Pascal is. 1 Pascal, this is going to be defined as a Pascal. Pascal is 1 Newton per 1 meter squared. Alright, well first, let's look at what 1 meter squared is. Okay, I got that tape measure. We're going to approximate it because that's what we're going to do. This is approximately 1 meter. Roughly to here. Then what we want to do to measure an area is we want to go perpendicular to that direction. Roughly the size of this whiteboard down to here. That is going to be 1 square meter. Roughly from there down to there. This particular area is going to be roughly 1 square meter. Pretty big. All this is going to be roughly 1 square meter. That's going to be the size. So now if I put a force, uniform all over this, of 1 Newton. Alright, well let's define what a Newton is. Newton is going to be a measure of force, and we know force equals mass times acceleration. If you didn't know that, well, it does. Force equals mass times acceleration, and now we have 1 Newton. Mass is going to be measured in the units of kilograms. Acceleration is going to be measured in the units of meters per second squared. The weight of something is going to be due to the gravitational acceleration. So, if we have a 1 Newton force, and we accelerate in gravity, we're going to approximate it as 10. It's really 9.8. But the mass that would result is force over acceleration. Force is going to be 1, the acceleration is 10, and we have 0.1 kilograms. 0.1 kilograms is equivalent to approximately 1 Newton. Therefore, 1 Newton is approximately equal to 0.22 pounds. So if I took 2.22 pounds and put 22 pounds of force over this whole area, it's not a very strong pressure. But that's in a nutshell what stress is going to be. If it was going to be tangent, I would apply it in this direction compared to that area. So, now that you have a little bit of understanding, or a better understanding what a Pascal is, let's talk about the viscosity mu and what a Pascal second actually means. All right. All right. So, if we have a fluid, a liquid, let's talk about. Actually, deal with gases, but it's easier to visualize with a liquid. If you take a fluid and place it between two plates, such as this, 2 plates, and if I add a liquid in between it, you can think of that as oil in between something in your car engine. I have 2 plates, each of 1 meter squared. So imagine, visualize these plates as being this large. If I have 2 plates that large, I put liquid between it, I'm going to have a thin, very thin distance between it. If I push with a stress of 1 Pascal, which is over this area about 2 or 0.22 pounds, 0.22 pounds in this direction, the plate will move a distance equal to the thickness of that liquid. Let's give some numeric values to various household fluids or liquids. So, chocolate syrup. About 1 PA second. Olive oil. We used to date olive oil. About 0.1 Pascal seconds. And water. About 0.001 Pascal seconds. Let's write this in scientific notation. 1 times 10 to the negative third Pascal seconds. Okay, after this lecture, watch the demonstration. And that's going to guide you with how you might want to set up your homework or home. Let's discuss what your homework is. Your homework is to pick 3 non-toxic household fluids. And compare how they flow down an inclined plane. Rank them by greatest to least viscosity and videotape your experiments. Once you get done with that, this is what I'm going to define for what viscosity is also known as. And using that definition, it might help become a little more clear what viscosity means. So, its resistance to flow is futile. Resistant to flow due to shear stress. High viscosity is going to be futile for the liquid to flow. High viscous fluids are also called thick, such as peanut butter. Peanut butter is considered to be thick, and it's going to have strong intermolecular forces. Alright, that concludes the first lecture, An Introduction to Thermal Fluids.